Let's study 9th standard ICSE chemistry chapter 4, atomic structure and chemical bonding. An atom is the smallest particle of an element which can take part in a chemical reaction, and it may or may not exist independently. There are 118 elements discovered so far. Oxygen is an element, whereas water is a compound. An oxygen molecule is made up of 2 atoms of oxygen. Let's write it as O2. Water, on the other hand, is made up of 1 atom of oxygen and 2 atoms of hydrogen. This is called Mickey Mouse. A molecule of water. Let's write this as H2O. But it's a false notion that a molecule is made up of 2 or more atoms. Now, this was a diatomic molecule. This is a triatomic molecule. But we can even have monoatomic molecules. For example, helium. Helium is made up of just 1 atom. It doesn't combine with any other atom. It's inert. It's stable. It's a noble gas. So this atom of helium itself is also called the molecule. You see, atoms may or may not exist independently. An oxygen atom cannot exist independently because it is unstable. Its outermost shell is incomplete. Its octet is not yet achieved. So it will always combine with some other atom of the same element or a different element to become stable, to complete its electronic configuration. And that's the whole reason why all the chemical reactions take place. Because each atom wants to be stable. But some people are born stable. They don't need anybody to settle down. They are single, not ready to mingle. Like noble gases, even noble metals, for example gold. It's monoatomic. In fact, all metals are monoatomic molecules. They can exist independently. So here this atom is also called the molecule. For compounds, we cannot have atoms. We cannot have an atom of water. We can only have molecules. So next, let's say glucose. So that molecule is C6H12O6. That's the smallest particle of this substance which exists independently. It has totally 24 atoms. On the other hand, chlorine is diatomic. So it will be a combination of 2 chlorine atoms because a single chlorine atom cannot exist independently. Ozone, on the other hand, is triatomic. You'll have 3 oxygen atoms combined. So now we know the difference between atom and molecule, and sometimes both of them may mean the same thing. And now we also know the difference between elements and compounds. Because here, each element is made up of same type of atom. But here, the compound is made up of 2 or more elements which can be broken down only with the help of some chemical process. This can be broken down into carbon, hydrogen, and oxygen. So this is not an element. Water can also be broken down into hydrogen and oxygen, for example, by electrolysis. So water is not an element. Now what is unique about each element is its atomic number. For oxygen, atomic number is 8. For helium, atomic number is 2. For gold, it's, I believe, 79. For chlorine, it's 17, and so on. Atomic number is simply speaking the number of protons in the nucleus, which will obviously be equal to the number of electrons because each atom is electrically neutral, and that's possible only if the number of protons and electrons are equal. That is, the number of positive charges and negative charges are equal. Let me draw the oxygen atom. First, we draw the nucleus. I said atomic number of oxygen is 8. That means it has 8 protons, positive charges, and so it should have 8 electrons. Now the first shell can only accommodate 2 electrons. That's the capacity. So how many electrons are left now? 6. That would be in the second shell. 1, 2, 3, 4, 5, 6. But the second shell can accommodate up to 8 electrons. So it needs 2 more electrons to become stable, to achieve its octet, and to become like the nearest noble gas, which is neon. So oxygen's electronic configuration is 2,6, whereas neon's electronic configuration is 2,8. How can it achieve this stability? Well, it just needs 2 more electrons. And it can get those 2 electrons either by gaining it from some other atom or by sharing it with some other atom. That's the reason why oxygen reacts with anything to become stable. But note how, after gaining the 2 electrons, its atomic number is still 8. even though the number of electrons will now become 2 plus 8, 10, but we still say atomic number is 8 because atomic number is the number of protons. Since now there is an imbalance between protons and electrons, this would have more negative charge because electrons are negative. So it will be charged 2 minus means or 2 negative signs here, and we call this an oxide ion, that is O2 minus. If it has gained 2 electrons, I'm not talking about when it shares 2 electrons. So the difference between an atom and an ion is that, number one, ion is charged, atom isn't. An ion has its outermost shell complete. An atom, it may or may not have its outermost shell complete. Ions can exist independently only in solution form or in plasma state, but atoms of elements may or may not exist independently. If it's a noble gas or metal, it may exist independently, otherwise it can't. Then what is atomic mass number? Atomic number is number of protons, but the mass number is the number of protons plus number of neutrons. So here it's 16. Oxygen's mass number is 16. But note that the number of neutrons is never fixed. It's possible that instead of 8, it has 9 neutrons. Then what would be the mass number? It would be 17. That's possible. That is called an isotope of oxygen, although it may not be stable. Isotope means atoms of elements having the same atomic number, but different mass numbers because they have different number of neutrons. Note that number of neutrons don't matter as far as chemical reactions are concerned, because in chemical reactions, the only thing that participates in the reaction is the electron, which depends on atomic number, not the mass number. And when we calculate the mass number, we are adding protons and neutrons. Why not the number of electrons? Because as I said, electrons hardly have any mass. So we can ignore that. Now, if I tell you that the mass number of chlorine is, let's say, 35, what does this information tell? Well, there is a lot I can say by looking at this. Atomic number is 17, means its electronic configuration is 2, 8, 7. It means it has 17 protons, it means it has 17 electrons. And it has 35 nucleons, that is protons plus neutrons. But out of that, 17 are protons. So how many neutrons are there? 35 minus 17? 18 neutrons are there. So I found the number of neutrons also. I can even draw the diagram of chlorine atom now. Chlorine nucleus will have 17 protons and 18 neutrons. Then the first shell will have 2 electrons. The second shell will have 8 electrons. You should draw all diagrams only with pencil and a compass or a pro circle. Freehand diagrams are not allowed. 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. And the third shell will have 7 electrons. So 1, 2, 3, 4, 5, 6, 7. So its last shell is again incomplete. It needs one more electron to become stable, which it can get by either gaining an electron from some metal or sharing an electron with some non-metal. That is why we say valency of chlorine is 1. In fact, after it gains, it will be charged. Its electrovalency is -1 because it will gain a negative charge. Non-metals always are electronegative. Their valencies, electrovalencies are negative. Whereas metals, they are electropositive. They always lose electrons. Non-metals gain electrons. Metals lose electrons. For example, let's take sodium. Sodium is 2, 8, 1. So sodium, 2 electrons, 8 electrons, and finally 1 electron in the last shell. In order to be stable, it would love to lose that 1 electron so that it becomes 2, 8 only, because that 1 electron is gone. That way, it will become stable like neon. So metals always lose electrons to become positive. So they are called cations after they become positive ions, whereas non-metals become anions, that is negative ions. So why are they losing or gaining electrons? To become stable, like the nearest noble gas. Now these orbits are also called energy shells because the electrons in each shell has a fixed amount of energy, and they are labeled as K, starting with K, L, M, N, and so on. And the number of electrons each can accommodate is given by the formula 2n squared. So if you ask me how many electrons are possible in the M shell, that is the third shell, let me use the formula and find out. 2n squared is equal to 2 into 3 squared is equal to 2 into 9 is equal to 18 electrons. Maximum 18 electrons are possible in the third shell. But if that's the case, what happens if I draw an atom of calcium? Let's see. Nucleus, just drawing the first shell, second shell, and third shell. Calcium's atomic number is 20. So let me draw 20 electrons. I've got 2 electrons in the first shell. I've got 8 electrons in the second shell. 1, 2, 3, 4, 5, 6, 7, 8. So then totally 10 done. How many electrons are left? 10 electrons are left. Well, the third shell can have 18 electrons, right? So I can easily fit 10 electrons in the last shell, correct? No. There is one rule. The rule says that whichever is the outermost orbit of an atom, it cannot have more than 8 electrons. That means here, if I fit it with 10 electrons, it's not allowed. I can only fit 8 electrons here. 1, 2, 3, 4, 5, 6, 7, 8. So now how many are left? 2 electrons. So that will go in the final shell, the fourth shell. Now the reason behind this will be explained in college level. You see, each shell has sub-shells, S, P, D, F, which is not there in school syllabus, so don't worry about it. You just have to know that there are certain rules to follow. And fortunately, we just have to know the electronic configurations of elements 1 to 20. That's all. So beyond calcium, things become a little strange. The transition elements, they don't follow the octet rule strictly. The octet rule simply means that you can become stable if you can have 8 electrons in the last shell. The duplet rule is applicable only to smaller atoms like hydrogen or helium, lithium. You see, hydrogen just has 1 electron in the last shell. So to be stable, it needs 1 more electron. And then the first shell, which is the last shell in this case, is complete. Here, the third shell has capacity for 18 electrons. But it can use this capacity only if it were the second last or the third last shell. If it is the last shell, it cannot have 18 electrons. So you see that if we know the atomic number, we know so many things. We can know the valency. Chlorine is -1. Oxygen is 2. Sodium is 1. So we should know the valencies of the first 20 elements. We should learn the entire table. Electronic configuration, the valency. Mass number need not be learned. And we should even know if it's a metal, non-metal, or a gas. You can see that if the valency is 1, 2, or 3, usually it's a metal. And if it's 4, 5, 6, the valence shell that is, then it is a non-metal. The valence electrons, when I talk about valence electrons, I mean the number of electrons in the last shell. So if the number of electrons in the last shell are 1, 2, and 3, we call it a metal. But if it is 4, 5, 6, 7, we call it a non-metal. And of course, if the last shell is complete, we call it noble gas. There are a few exceptions though. For example, boron is a metalloid, and so is silicon. So remember these two exceptions because they have properties of both metals and non-metals. It's a transition between metallic and non-metallic properties, so we call it metalloid. Now, about isotopes, as I said, they are atoms of the same element having the same atomic number but different mass numbers because the number of neutrons are different. Now, since they will have the same electronic configuration, 2,6, 2,6, the chemical properties will be same because chemical properties only depend on the electronic configuration, that is the valency. But the physical properties may be different. Since oxygen 18 is a little heavier than oxygen 16, there will be a difference in their boiling point, melting point, a slight difference. But electronic configuration is same. It's 2,6 here and 2,6 here. Valency is also 2 and valency here also is 2. So the chemical properties are same. Sometimes atomic mass on average may be a decimal value. For example, chlorine's mass is taken as 35.5 because we have 2 isotopes of chlorine available, chlorine 35 and chlorine 37. This one has 18 neutrons, this one has 20 neutrons. But the percentage of chlorine 35 is more in nature. So if you take a weighted average, then we say that its mass number is 35.5. How that average is calculated, that is not in syllabus. Now let's understand how ionic compounds are created. Now look at sodium and chlorine. Sodium has 1 electron extra and chlorine has 1 deficient electron. To become stable, sodium will donate 1 electron. You see, metals always give electrons, and giving of electrons is called oxidation, that is losing electrons, and gaining electrons is called reduction. So sodium forms a cation and chlorine forms an anion. Make sure you write the brackets also. This is called the cross and dot structure, where the dots represent electrons. So now both of them are stable, 2,8, 2,8,8. They have acquired the electronic configuration of the nearest noble gas. However, now they are charged and opposite charges attract each other. So they stick to each other to form NaCl. A molecule of sodium chloride is formed, and since there are ions involved, it is called an ionic compound or an electrovalent compound. Similarly, for calcium oxide, Calcium loses 2 electrons, oxygen gains 2 electrons, calcium becomes a cation, oxide is an anion, and they are attracted to form calcium oxide. Remember that ionic compounds are formed between metal and non-metal. But what if there are two non-metals? Non-metals don't donate electrons. Non-metals share electrons. So here, transfer of electrons is not possible. If you look at nitrogen, nitrogen's electronic configuration is 2,5 and 2,5. Each of them requires 3 electrons to become stable. But neither is willing to donate their 3 electrons. So what they will do is, they will share the electrons. Because sharing is formation of covalent compounds. And the bond is called covalent bond or molecular bond. There are no ions formed here. There is no positive or negative charge here. Since they are sharing 3 pairs of electrons, it's called a triple bond. Let me show how water molecule is formed. So we have this oxygen atom. This is a nucleus. The first orbit has 2 electrons. Yes, all orbits have to be shown compulsorily. And this one has 6 electrons. 1, 2, 3, 4, 5, 6. It needs 2 more electrons to be stable. And all it has are hydrogen atoms nearby. And they are not willing to give electrons. They are not so generous as metals. They also want 1 electron to complete their duplet and achieve the electronic configuration of the nearest noble gas. For them it is helium, and for her it is neon. So when they combine, let's see what happens. This is a nucleus, by the way. 2 electrons, second orbit, 1, 2, 3, 4, 5, 6. And let me draw a hydrogen atom. You have to draw this with a compass or with pro circle. You cannot draw it freehand. Hydrogen's electron here, hydrogen's electron here. So you can see that now oxygen seems to be having 8 electrons in a last shell, so it's stable. Hydrogen seems to be having 2 electrons in its last shell, so that is also stable. So see, the atoms have become stable by cooperating with each other, and here we say that hydrogen single bond oxygen single bond hydrogen. So there are 2 single bonds. 1 bond simply means a pair of electrons are shared. And covalent bonds are formed only between nonmetals.
9th Standard ICSE Chemistry, Concise Textbook, Chapter 4. Exercise 4A is entirely cancelled. Let's start with 4B, Atom and its structure. We know that the nucleus of an atom is made up of nucleons, that is protons and neutrons, and electrons are in shells around the nucleons. This table tells us the properties of subatomic particles. Just 3 of them. By the way, there are more than 200 subatomic particles, but in our syllabus we have only these 3. Study their symbols with the subscripts and the superscripts. The subscript tells us the charge, so electron is negatively charged, proton has positive charge, neutron is neutral, no charge. And the superscript tells us the mass, electron is almost massless, proton has a mass of 1 AMU, that is atomic mass unit, and neutron has a similar mass of 1 AMU. This is a representation of an atom. The actual atom is quite different from this, but at school level we learn it as a planetary model. These are the definitions of nucleus and orbits. Atomic number is the fundamental property of an element because this decides the number of electrons, because in a neutral atom the number of electrons is equal to the number of protons. So the atomic number will decide the electronic configuration, and that will decide the valency, and that decides all the chemical properties of that element. The significance of the atomic number is that it tells us the number of protons, electrons, and the amount of positive charge in the nucleus as well. The mass number is the total number of protons and neutrons. Electrons are not counted here because they are almost massless. Mass number is always a whole number, whereas atomic mass or atomic weight may not be a whole number because it is counted in atomic mass units. Electronic configuration is simply how the electrons are distributed in different shells. Now there are 2 rules to follow. Rule number 1, the maximum possible number of electrons in any shell is given by the formula 2n squared. For example, L shell is a second shell. So 2 square is 4 and 2 into that is 8 electrons. So the second shell can have maximum 8 electrons. Third shell can have maximum 18 electrons, and so on. The second rule says that no matter what the capacity, but if the last shell has been mentioned in the structure, then it can have maximum 8 electrons. That is why calcium is 2882. It cannot be 2810. Even though the third shell can accommodate up to 18 electrons, we cannot write it as 2810 because that would be against the second rule, which says that the last shell should have maximum 8 electrons. Hence we push 2 electrons to the fourth shell, 2882. So metals usually have 1, 2 and 3 valence electrons, whereas non-metals have 4, 5, 6, 7 valence electrons. This table has to be learnt, but not the mass number. If I know the atomic number, that is the same as the number of protons. And number of neutrons is nothing but mass number minus atomic number. The electronic configuration can be found out by knowing the atomic number. You should know the first 20 elements with the atomic number and their valency. Valency of hydrogen is 1 because it would like to acquire one more electron to become stable like the nearest noble gas, which is helium. Helium is a noble gas, which means it's inert. It doesn't react because it has only one shell with 2 electrons, so its last shell is complete. So it will neither take, give or lose electrons. Hydrogen is a non-metal, it's a gas. Boron and silicon are metalloids, that is, they have properties of both metals and non-metals. Lithium is a metal, valency is 1 because its electronic configuration is 2, 1. So the second shell has 1 valence electron. It would like to lose it so that it becomes stable like helium. But in that process, it will be deficient in 1 electron and it will acquire a positive charge and become a cation. Remember, metals are always electropositive. They give electrons during chemical reactions and they become cations. So positive people always give and negative people always take. So non-metals are always electronegative. They take electrons when reacting with metals to form anions because now they have extra electrons, and extra electrons means they have more negative charge. For example, oxygen, atomic number is 8. So electronic configuration is 2, 6. In order to be stable like the nearest noble gas, which is neon, it would like to acquire 2 electrons so that it becomes 2, 8, and the last shell will be complete. Octet will be complete. It's a non-metal because it takes 2 electrons and becomes negatively charged. Oxide anion 2- is formed that way. Similarly for magnesium, atomic number is 12 and the valency is 2. So we need to know the valency of all the first 20 elements. Sometimes variable valency is possible, but not in the first 20 elements. I also see that the mass number may be different because number of neutrons may be different, like in the case of chlorine. They are called isotopes. More about it soon. Now let's start with 4b, 4c part, valence electrons. The number of electrons in the last shell are called valence electrons. The last shell is called valence shell. We know that metals always lose electrons. So they are good reducing agents because they themselves undergo oxidation. Losing electrons is called oxidation. So remember, metals always lose electrons to become cations. This is an ionic equation. What is an ion? An electrically charged atom or group of atoms is called an ion. This is a cation, positively charged. Why? Because 1 electron was lost so that it could achieve the electronic configuration of the nearest noble gas, which is neon. But in that process, now it has 11 protons left. Remember, number of protons never change, number of electrons change during a chemical reaction. So it has 1 deficient electron, or you can say number of protons are now 1 more than the number of electrons. Hence it is positively charged. And that is why it's a reducing agent. Non-metals, on the other hand, always gain electrons. They're electronegative. They acquire a negative charge. They become an ion. Addition of electron is called reduction. But they oxidize the metals. So they are good oxidizing agents. This is hypocrisy. They themselves undergo reduction, but they oxidize others. Then we have the definition of valency. Go for the modern definition. That is the number of electrons lost, gained or shared during a chemical reaction. Valency of noble gases is obviously 0. All noble gases have a complete octet except helium. Helium has only 1 shell which can have maximum 2 electrons, so it follows the rule of duplet and it is stable. The last shell is complete. All other atoms react simply because they would like to be like noble gases. Cancel this paragraph. There are various ways to become stable. Either share electrons and form a covalent bond or transfer electrons and form an ionic bond. More about this in future sections. Now let's talk about isotopes. This paragraph is cancelled. Let's learn the first 3 examples. Here in hydrogen, I see that the number of protons is same and the number of electrons is same, valency is same, chemical properties are the same. It's just that the number of neutrons are different. 0 neutrons, 1 neutron and 2 neutrons. Well, the number of neutrons, that is the atomic mass number, doesn't really matter in chemical reactions. It matters in nuclear physics and nuclear chemistry. Since they have the same atomic number and same properties, they are called isotopes. It's just that this is heavier than this and this is heavier than that. So their physical properties may be different because their mass numbers are different. Similarly, in carbon, we have same number of atomic number, same number of protons, but the mass number is different because number of neutrons are different. But chemically, all of them are carbon. In fact, carbon-14 is very useful in radiocarbon dating. You see, these heavier versions of the element are quite unstable. They will decay radioactively to become the lighter versions of some other element. That is nuclear chemistry, which we'll study in the future. So these are called radioisotopes, which gives out rays like alpha, beta, gamma, etc. And these radiations can be useful for us. For example, carbon dating helps us to know the age of a fossil or any archaeological specimen. These rays can also be used to treat cancer. Now, chlorine is available in two varieties, chlorine 35 and chlorine 37. So this is usually heavier than this, simply because number of neutrons are more. And that is why, on average, we take the atomic weight of chlorine as 35.5, because this is 75% of all the chlorine in the world. This is 25%. Then we have a give reason why the chemical property is same and the physical property is different, which I've just explained. This definition is cancelled. Uses, let's learn 3 of them. Cancel the 4th and 5th. Here they explain why sometimes we get a fractional atomic mass. Isobars, that's some extra information for you. Here there are 2 atoms with same atomic mass but different atomic numbers. They are 2 different elements, no same chemical properties. Number of protons are different, number of neutrons are also different. Here we have 18 protons and 22 neutrons. Here we have 20 protons and 20 neutrons. The only thing matching is the number of nucleons, that is atomic mass number, is the same. So they are called isobars. No, that's not the hanging place for isotopes.
Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.